Today we're going to start with the chapter of temperature. So these are the learning outcomes that we need to cover in this topic, and we're going to cover each one of them. Firstly, what do we mean by temperature? So temperature is the measure of the degree of hotness or coldness of an object. How hot or cold an object is, and the SI unit for temperature is the Kelvin, but more commonly the degree Celsius is used to measure temperature. Now, there's a difference between temperature and heat. We discussed the temperature is how hot or cold an object is. And so, heat is the amount of thermal energy that is being transferred from a hotter region to a colder region. When two objects are in contact and they have different temperatures, then the energy that is flowing, the heat energy that is flowing from the hotter object to the colder object is heat. The SI unit, as we discussed for temperature, is Kelvin, and since heat is a form of thermal energy, so the SI unit for heat is the joule. How can we measure temperature? So we'll use thermometers for that, and we have different type of thermometers that we're going to discuss. What are the qualities of a good thermometer? Firstly, it should have an easy to read scale so that it can be used easily, and it should be safe to use. It should be made of a material that is safe for daily everyday use. It is responsive to temperature change. We'll discuss what we mean by responsiveness and sensitivity. It is sensitive to small temperature changes, and it is able to measure the required range of temperatures. So if we are in the hospital, so then the range of temperatures is going to be around the body temperature. So for example, from 80 degrees till 110 degrees would be enough to measure for a clinical thermometer, since that is covering the range of human body temperature. But if the thermometer is used to measure the temperature of, say, a gas furnace, or very or other places like that, then we will be requiring thermometers with a much greater range. Okay, now how can we construct a temperature scale? First, we are going to choose an appropriate thermometric substance. What is a thermometric substance? A thermometric substance is one that has physical properties that will vary uniformly and continuously and linearly with temperature. What does that mean? When a thermometric substance, for example, mercury is a thermometric substance, because when I will increase temperature, the volume of mercury will also increase. That is why it is rising in the thermometer. And so if I am increasing the temperature, the volume of mercury will increase linearly at the same ratio. So it's a fixed amount at which it will expand, which is why I can use it in a thermometer, since it is going to expand at a fixed volume for every temperature change. Now, let's have a look at some thermometric properties and how they're used in thermometers. So, a volume of a fixed mass of a liquid is a thermometric property any substance can have. And an example is a mercury in glass thermometer and an alcohol in glass thermometer. This is because mercury and alcohol are both thermometric substances. The volume of mercury and alcohol is rising linearly with temperature. It's rising continuously with temperature, which is why I can easily use it to detect temperature changes. And a resistance thermometer makes use of the thermometric property of the electrical resistance of a piece of metal. So if a piece of metal has an electrical resistance, we can use that property in a resistance thermometer, because the resistance of that substance, of that metal, will increase or decrease uniformly, linearly, and continuously with temperature. Then we have electrical voltage, which is also known as EMF, the electromotive force. This is also known as voltage. So where is this used? It's used in a thermocouple thermometer, which makes use of the changes in the potential differences of two substances. Now, how do we construct a temperature scale? Now that we've chosen thermometric properties, we've chosen suitable thermometric properties, we need to construct the scale. So we'll take the example of a liquid in glass thermometer. More commonly used example is a mercury in glass thermometer. And so we'll construct its temperature scale. We chose an appropriate thermometric substance. Now we're going to calibrate the thermometer. So for calibrating a thermometer, we first choose two fixed points. What are these fixed points? The ice point and the steam point. Why do we choose these? Because these are the most commonly used points, the melting point of water and the boiling point of water. So the melting point of water is 0 degrees Celsius, so that's my ice point. It's a lower fixed point that it will remain same every time. And the steam point is the upper fixed point, that is the boiling point of water, which is 100 degrees Celsius. So these are used as two reference points. And then I'm going to divide these intervals between 0 and 100. I've marked my ice point and my steam point. There's a difference of 100 degrees between 0 degrees Celsius and 100 degrees Celsius. So I will divide that into 100 parts, and each interval becomes 1 degree Celsius. And so the change in the length of mercury thread is the small is the rise of mercury. It's how much the mercury is rising. That red line is known as the mercury thread. It is proportionate to the temperature change, which means that the change in the volume or change in the length of mercury is varying linearly or continuously with a change in temperature. How do I determine the ice point? I will place my thermometer into melting ice. Now, as soon as the ice starts melting, I will record the temperature and I will wait for that for the level of mercury to be stable and to be on 1 point. When that level is reached, then I'm going to mark it as my ice point or as 0 degrees Celsius. So first I immerse the bulb, the lower part of the thermometer, into a funnel that has melting ice. Then when the level was steady, then I made a mark L0, which means that the length of the mercury thread at 0 degrees Celsius, that becomes my ice point. And so now what is left is the steam point. For the steam point, I'm going to measure the temperature of steam. So I am not going to record the I am not going to record the temperature of the water. Why? Over here I placed it inside the ice, but here I'm going to place it in above the water. I have to make sure that it is above the water because I want to record the temperature of the vapors. Now the boiling water, you boil water and you need to ensure that you have a specific pressure, so you're going to use a manometer to ensure that. Now the water is going to rise, you're going to measure the temperature of the vapors, you're going to let it come steady, and when it is steady, then you're going to mark it as your steam point. So the bulb should be just above the boiling water, we discussed that, and then the stem should protrude outwards. Why? So that you can read the temperature. And then when the mercury level is steady, you're going to mark L100 over there, the length of the mercury thread at 100 degrees Celsius. This is your steam point. Now, for example, you need to calculate temperature. So this is the information that has been given to you. You need to find the length of mercury thread L0 at 0 degrees Celsius. Then you find the length of mercury thread at 100 degrees Celsius, and then you find the mercury thread at an unknown temperature. So what are the three things you need to do? Firstly, you are going to place your thermometer. You have an unknown temperature. For example, you have a liquid that has a temperature you want to find out and you don't know what the temperature is. You first place your thermometer in ice, in melting ice, as we discussed the apparatus right now, and then you'll mark the ice point. So then you will find the length of mercury, how much did the mercury rise, and then you're going to place it in above boiling water. You're going to mark the steam point and you're going to find the length of the mercury thread at 100 degrees Celsius. And then you'll find it for unknown temperature. How will you do that? When you have two lengths already, you can use the equation theta, the unknown temperature, is equals to length of the thread at unknown temperature minus the length of the thread at 0 upon length of the thread at 100 minus the length of the thread at 0. So for example, at 100, it's 40, and at 0, it is 5, and at theta, it is 25. the length. Now what will you do? You have the length of theta as 25. The length at 0 is 5. So 20 upon 100. The length at 100 is 40 minus the length at 0, which is 5. So it becomes 20 upon 35 into 100. 20 upon 35 into 100, when you're going to calculate that, you're going to get the temperature in degrees Celsius for the unknown liquid. That's how you can measure unknown temperatures. Now, what is the general equation for calculating temperature? This was using length, but we can generally use any physical property to calculate that. What if we didn't have length? What if we had resistance? So we will our formula will then become r theta minus r0 upon r100 minus r0 into 100, because this formula can be used for any thermometric property. This is x theta minus x0. This is x100 minus x0, the two values that we are dividing with each other, and then we multiply it by 100. So theta is equals to this formula, and in place of x, you can put length, resistance, or any thermometric property. Now let's move on to the resistance thermometer. So the resistance thermometer consists of a platinum wire, and that is coiled around a piece of mica in a silica tube. That's all you need to know about the construction of a resistance thermometer. And it uses the thermometric property electrical resistance of any substance. Now the resistance of the wire is varying continuously with temperature over a range of values. We discussed that. And so how are we going to calculate temperature with a resistance thermometer? We'll use the same formula we just discussed, because um, we can use that for any thermometric property. The resistance is going to be in ohms. The length that we discussed earlier was in centimeters or millimeters, and the resistance is going to be in ohms. Now we have a thermocouple thermometer that uses the property of EMF. So a thermocouple consists of two wires made of different metals such as iron and copper. We're going to have a look at the image of a thermocouple, but right now we need to know that the metals should be two different types of metals. Why? Because we need to generate an EMF, we need to generate a potential difference, and that difference will only be generated when we have two wires made of different metals, for example iron and copper. Now you will take two wires of two different types, and you're going to join them at the ends, so that makes two different junctions. And then when you put them in liquids or in any place with two different temperatures, a temperature difference is generated due to a difference in potential difference. How do we calculate temperature with a thermocouple? You have a relationship E is EMF, is directly proportional to delta theta. Delta theta is the temperature difference between the two junctions. So we're going to use the ratio method over here. Now, before we move on to an example of thermocouple, let's move on to an example of resistance.
I just give a formula wali slide.
So we know the formula, that is R theta minus R0, the resistance at unknown temperature minus resistance at 0 upon resistance at 100 minus resistance at 0. So the resistance at the unknown temperature is 1260 ohms. At 0 it is 450 ohms, and at 100 it is 560 ohms. So then if we put in the values in the formula, it becomes 1260 ohms minus 450 ohms upon 560 minus 450 ohms, and you multiply it by 100. R theta, unknown resistance, 1260, R0, resistance at 0, or the steam point, it's 450 upon 560 minus 450. Sorry, this is for the ice point, not the steam point. And consequently we get our temperature as 736 degrees Celsius. Then we have another question over here. They're saying that you need to determine the temperature when the length of the mercury thread is 12 centimeters from the negative 10 degrees Celsius mark. This is very important to visualize. So you have a thermometer that has a range from negative 10 degrees Celsius till 110 degrees Celsius. It can measure negative 10 degrees Celsius and it can measure up to 110 degrees Celsius. So that means it has a range of 120 degrees Celsius. Negative 10 से लेके 0 तक you have 10 degrees Celsius. From negative 10 to 0, 10 degrees Celsius. And then from 0 to 110, 110 degrees Celsius. So 10 plus 110 gives you 120. So the range is 120 degrees Celsius. Because the range is the difference between the maximum and the minimum point. Then the length of the mercury thread between negative 10 and 110 marks on the stem is 20 centimeters. So for a range of 120 degrees Celsius, the length of the stem is 20 centimeters. So if for 120 degrees you have 20 centimeters, then 120 upon 20 gives you the length for every degree Celsius. Now you need to determine the temperature when the length of the mercury thread is 12 centimeters from the negative 10 degree mark. 12 centimeters from the negative 10 degree mark, and we need to know the temperature. So let's see how this actually looks. You have a thermometer that's measuring from negative 10 till 110. So that means, and the distance is 20 centimeters. You have a unknown temperature theta at a point, and the distance is 12 centimeters. We've been given in the question. From the negative 10 degree mark, it says that the length is 12 centimeters. Now we need to calculate theta. This does not require any formula. This just requires proportion and cross multiplication. So if 20 centimeters per, you can cover 120 degrees Celsius. From negative 10 to 110, we discussed that 120 degrees Celsius are being covered. So from 12 centimeters till what are you getting? What is the value you are getting? That is 12 upon 20. That is the proportion. For 12, we are going to cross multiply. So 20 is to 120 degrees Celsius, and then 12 is to x degrees Celsius. When we cross multiply, we get this. But the thing is that when we are getting the value through this, it's 72 degrees Celsius. But theta is not 72 degrees Celsius. Why? Because 72 degrees Celsius is the value for 12 centimeters. Since it's 72 degrees Celsius, from the negative 10 degree mark, we're going to add that negative 10. And so 72 plus negative 10 will give me 62 degrees Celsius. And so theta is 62 degrees Celsius. Let's have a look at another example, that is of the thermocouple thermometer. So this is how a thermocouple looks like. You're using this to measure the EMF, and this is a voltmeter, and you have two junctions. You have two different wires. This is one wire and this is one wire. They both are joined at two junctions, X and Y. Both of the wires are made of different metals. And so if we want to find an unknown temperature, what do? We first place X at 0 and Y at 100, and then we have an unknown temperature. So 0 and 100 are the 0 and 100 are the ice and steam points. Now you're placing the hot junction in the new unknown temperature. So then Y go, you remove it from 100 and you place it in a new temperature that you don't know, in temperature X. And then through that you can find out the actual temperature. So what is actually happening? First, at the ice point and the steam point, you are finding the EMF, the potential difference that is generated in volts, and then placing it at 0. And you will always put the hot junction in the unknown temperature. So then placing it at 0 and 100, you get a reading, and then at 0 and an unknown temperature, you're getting another reading. So that's how you can find out the unknown temperature. Why am I using a thermocouple over here? Because a thermocouple is, we're measuring it in a gas turbine. A gas turbine is very large and hot, and so here it's pretty useful because it helps me measure temperatures that are very high it measures temperatures rapidly, and it measures temperatures that are difficult to um, record, that are in places which are high up in, for example, creeks, etc. So what does the first question say? It says, why is a thermocouple suitable for measuring the temperature in a gas turbine? And secondly, it says, calculate the temperature in the gas turbine. So for the first one, the answer is that the thermocouple is responding quickly to temperature changes. It also measures high temperatures, and it measures temperatures in hard to reach locations. So we have three reasons why we're using a thermocouple. It responds quickly to temperature change, it is able to measure high temperatures, and it measures temperatures in hard to reach locations. For the second one, so at when it's kept at 0 and 100, when the two junctions x is at 0 and y is at 100 degrees Celsius, the EMF generated is 45. But when you place it at 0 and an unknown temperature, so the EMF changes to 65 millivolts. So these are all the values that we have. How are we going to use it to calculate? We have the relationship E is directly proportional to delta theta. The EMF is directly proportional to the change in temperature. So 45 millivolts was the EMF initially, is equals to K into 100 degrees Celsius. What is K into 100 degrees Celsius? K is a constant that is used. So that is the formula we use. E is equals to K into delta theta. And so 65 millivolts is equals to K into delta theta. We don't know. So in the first one, using this relationship, we derived a formula. E is equals to K into delta theta. What is what is K? K is the constant and delta theta is the change in temperature. K is any constant we have. Now, in the first scenario, we discussed that when x and y were at 0 and 100, the EMF was 45 millivolts. So at 45 millivolts, you got a temperature difference of 100. How? 100 minus 0 is equals to 100. The temperature difference is 100 degrees Celsius. Then in the second scenario, it changed to 65 millivolts is equals to K into delta theta. We don't know what is delta theta. We don't know the change in temperature because the one junction was at 0 and the other junction was at an unknown temperature. Then what do? You are going to again use ratio. At 45 it's 100 degrees Celsius, and at 65 it's delta theta. You don't know the change, so delta theta becomes 144 using this. How did you do that? At 45 millivolts the change in temperature was 100. At 65 millivolts the change in temperature you did not know. Now the change in temperature is 144 degrees Celsius. We want to find the unknown temperature. How do we know that this is the unknown temperature? Because what will be the change in temperature? Now the change in temperature is 144. So that is the temperature at junction Y. The temperature at junction X is 0. So 144 minus 0 is giving you 144. So the final answer is 144. Now let's have a look at past paper questions. So the first question says that the diagram shows two thermometers P and Q that are identical except that P contains less mercury. Apart from that, they're same. Now we have some options. Which statement is correct? The lowest measurable temperature is same on P and Q? No. Why? Because when you have lesser mercury, it's going to expand less for the same temperature rise, and so the lowest measurable temperature, the range will be different for both. Why? What is the range? Range is the difference between the maximum and the minimum temperature. What is sensitivity? Sensitivity is the temperature, is the distance covered by the mercury thread at a change in temperature. What is what is responsiveness? How fast the thermometer is responding to a temperature change. Now how can we increase the range? We can increase the range by decreasing the size of the bulb. by increasing the diameter of the capillary bore and by increasing the length of the stem. These are three ways we can increase the range. How can we increase the sensitivity? We can use a larger bulb. Larger bulb will have more mercury. Having more mercury means it will expand more, so sensitivity increases. You can also have a less diameter of a capillary tube. How will you increase responsiveness? You'll use a smaller bulb and a thinner wall. Why? In a thinner wall, it can respond quickly to the temperature change. The temperature has to, the energy has to travel a smaller distance, and by using a smaller bulb, when you have lesser mercury, so it's going to respond faster. Now the question, A part is incorrect. The second part says that the range of P is equal to the range of Q. That is also not true. Since the first part is incorrect, the lowest measurable temperatures are different, so automatically the ranges are also different. The scales on P and Q are both linear. That is correct. The amount of mercury used does not change the fact that the thermometric substance will stop varying linearly and continuously. Mercury will always vary linearly and continuously, so the scales will always be linear, which means that they will always be equal, the intervals, and the change in the length for every temperature change. D, the sensitivity of P is equals to the sensitivity of Q. Wrong, since when they're rising at different lengths due to different amounts, so Q will be more sensitive because it has more mercury, and P will be less sensitive. The next says that there are two identical thermometers, just that their liquids are different, so that is going to change their sensitivity and range. Now, there is the same temperature change, but in X, the volume increases more, and in Y, the volume increases less. Which is more sensitive and which has the larger range? X is more sensitive. Why? Because sensitivity is the increase in the volume or the increase in the length of the stem per change in temperature. So since X is increasing more, since the length of X is increasing more, the volume is increasing more, X is more sensitive. And in Y, the thermometer has the larger range. Why? Because if the liquid is rising less for every temperature range, that means that it can cover more degrees. If, for example, a thermometer rises 10 centimeters for 100 degrees Celsius, but another thermometer rises 5 centimeters for 100 degrees Celsius. That means that 5 centimeters more at 10 centimeters, it will be at 200 degrees Celsius. So in the first one at 10 centimeters, it's at 100 degrees Celsius, and at the second one at 10 centimeters, it's at 200 degrees Celsius. So automatically the second one has the larger range. So that's why Y has the larger range. And then the last question is from theory. So the first question states, what is meant by range? Range is the difference between the maximum and minimum points. What is sensitivity? Sensitivity is the distance moved by the thread per unit temperature rise. Why? How is this? How does this have a high sensitivity? What feature does it have that has high sensitivity? We can give two answers for that. Either that it has a larger bulb, which means more mercury, which means there is a greater increase in volume, hence high sensitivity, or we can say it has a narrow bore, so that it covers a greater distance for a given increase in volume. Then the next question states, what is the purpose of the constriction in the clinical thermometer? So the constriction is used to prevent the backflow of the liquid. This mercury can move backwards as well, so we need to prevent that. That's why we have a constriction over here. And then C part is related to the kinetic molecular theory. How does an increase in temperature produce an increased reading on the thermometer? There are 3 points to mention here. The molecules are gaining kinetic energy, hence they start to move faster. Then they move apart from each other, and then mercury expands upwards in the tube.